Welcome to Engineering Simplified. How do engineers make a motor run at half speed without changing anything about the motor itself? The answer is a variable frequency drive, one of the most widely used devices in industrial electrical engineering. Let's break it down. Remember that an AC induction motor's speed is set by the frequency of its supply through the synchronous speed formula, 120 times frequency divided by the number of poles. On a fixed 50 or 60 Hz mains supply, that means a standard motor only really has one natural running speed. A variable frequency drive exists specifically to break that limitation. A VFD takes in fixed frequency AC from the mains and outputs a completely new AC waveform to the motor at whatever frequency the application actually needs, and the motor's speed follows accordingly. Inside, a VFD does this in 3 stages. The first stage is the rectifier, which converts the incoming AC supply into DC using diodes or thyristors to flip the negative half of the waveform positive. That DC then feeds into the second stage, the DC bus, a bank of capacitors that smooths the rectified voltage into a clean, stable DC supply ready for the final stage. The third stage is the inverter, built from fast-switching transistors called IGBTs. These rapidly switch the DC bus on and off in a pattern called pulse width modulation, synthesizing a new AC waveform at any frequency required. If you're enjoying this, like, comment and subscribe, and check out the other Engineering Simplified playlists. By varying that output frequency, the drive directly controls the motor's synchronous speed. Drop the frequency to 25 Hz on a motor rated for 50, and its speed roughly halves. But frequency alone isn't enough. A VFD also adjusts output voltage in proportion to frequency, keeping the volts-per-hertz ratio roughly constant, so the motor's magnetic flux stays at its designed level. Without that voltage adjustment, dropping frequency without also dropping voltage would push the motor's core into magnetic saturation, causing excessive current draw and serious overheating, even though the motor is running slower. This V over Hertz control is exactly why VFDs are so much more sophisticated than simply cutting voltage with a dimmer switch, which would just make a motor struggle rather than genuinely slow it down. VFDs bring real, measurable benefits. For fans and pumps, power consumption scales with the cube of speed, so dropping speed by even 20% can cut energy use by roughly half. They also enable soft starting, ramping frequency up gradually from 0 rather than slamming the motor straight onto full mains voltage, which dramatically reduces inrush current and mechanical stress on startup. That gentler start extends the working life of belts, gearboxes and couplings, while also reducing voltage dips on the wider electrical network every time a large motor starts up. Beyond speed control, VFDs enable precise process control. Conveyor belts running at an exact speed, pumps maintaining constant pressure, or HVAC fans automatically responding to real-time building demand. Most VFDs also include built-in protection, overcurrent trips, motor thermal modeling, and the ability to ramp down gradually instead of cutting power instantly, avoiding the mechanical shock of a sudden stop. Many drives can also run a motor in reverse simply by swapping the phase sequence of the synthesized output waveform electronically, something that would otherwise require physically rewiring the motor's supply. The common mistake is assuming a VFD simply throttles power to a motor, the way a light dimmer throttles a bulb. It doesn't reduce power directly, it changes frequency, and torque and speed follow from that. Push a VFD's output frequency above the motor's rated frequency, and voltage typically can't keep rising to match, weakening the volts-per-hertz ratio and reducing the torque still available at higher speeds. So remember, a VFD rectifies AC to DC, smooths it, then resynthesizes a new AC waveform at a controlled frequency and voltage, and the motor's speed simply follows that synthesized frequency. That combination of energy savings, gentler starting, and precise speed control is exactly why VFDs have become standard equipment across pumps, fans, conveyors, and compressors throughout modern industry. Drop a like, comment the topic you'd like to see explained next, and subscribe. It genuinely helps this channel grow. See you in the next Engineering Simplified video.